Yes, any questions? Now, if you remember, we were discussing the Lorentz transformations. We had seen that if we define the 4-vector x mu, its 0 component was Ct, and the other 3 components are nothing but the ordinary position of our object. If we define such a quantity that we will be calling the 4-vector, from one reference frame to another reference frame, it just changes according to such an expression. Where this lambda mu nu matrix, we had seen that it was given by gamma minus beta gamma minus beta gamma gamma 1 1 and zeros over here. And this is what we call the Lorentz transformation. And we will see that we will call any quantity, any 4 quantities that transforms in this way, we will call it a 4-vector. Just like in the case of ordinary vectors, we know that under rotations, how the position vector changes if you rotate your coordinate axis, let's say. And any 3 numbers that change in exactly the same way as the position vector, we call them vectors. Now here, this is the position 4-vector. In general, we will say the position, although it contains also the time. This position 4-vector transforms in this way, and any 4 numbers that transform like this as you go from one reference frame to another reference frame, we will call them 4 vectors. And the interesting thing about this Lorentz transformation is that if you define, we had seen that minus c squared t squared plus r squared, which we will write in this form, x mu x0 minus r, no, plus r, sorry. This is invariant. The only difference between the upper index x0 and the lower index x0 is that the lower index x0, we will just define it to be minus ct. So we define this quantity, another 4-vector, with lower indices. This is called minus CTR. This is how we define them. And these have special names. If you have a 4-vector whose indices are at the top, we call it a covariant vector. Meaning that co basically means together. So if you have a 4-vector whose indices is up, it is a 4-vector that transforms just like the position vector. And then we have these lower indices. These are what we call the contravariant. If you have a 4-vector that has the lower indices, it changes in such a way that if you multiply it with the position vector, it cancels the change in the position vector. So in that sense, you see here I have a covariant vector, the product of a covariant vector and the contravariant vector. So this under a Lorentz transformation, or as you go from one reference frame to the other reference frame, this 4-vector changes like the position. Well, it is the position. And this 4-vector changes in such a way, in a sense, against the changes in this covariant vector. That's why it's called the contravariant. It cancels the changes in this one so that this product is invariant. So this is what we had done until last week. Now, any questions up to here in these Lorentz transformations?
Doctor, last week you had said that x0 is equal to ct, but
No. You see, keep in mind whether it is an upper index or lower index. x0 is ct, x lower index 0 is minus ct. They are different. This is minus x upper index 0. So these covariant vectors and contravariant vectors, they differ in the sign of the 0 component. By the way, just keep in mind, you see, when we are talking about scalar products or the magnitudes of vectors in three-dimensional space, they were always positive. There is basically no choice over there. But when we are talking about four vectors, their square, we had seen that they can be both positive or negative. So what this means is, just like this is invariant, this is something invariant, but this is also invariant. Both of these things are invariant. I can define the position vector squared to be this one, or I can define the position squared to be this one. They are just equally valid because both of them are invariant. We can define the scalar product of two four vectors either in the first form or in the second form. They will be both invariant anyway. This is just a convention. Your book prefers to use this convention. So that it's the t squared that is minus. In particle physics community, for example, if you work on particle physics, the convention that I'm used to is this one. This is the convention that I use most of the time. If you study gravitational physics, gravity or cosmology, they use this metric. This is called the metric. This is how they define the square. It doesn't make any difference. So it's just a choice. I mean, in three-dimensional space, there is basically no choice because for only one choice, we have a positive amplitude square. But since here, there is no such restriction, let's say, the square of any four vector can be both positive or negative. So basically, there is no reason to choose one definition over the other definition. This is just so that if you see in some other place that you define it in this way, just don't be confused. In that convention, x mu is CTR, and if you just lower the indices, it's the position that acquires the minus sign. In the convention used in the book, x mu is CTR, and if you lower the indices, it's the time component that changes its sign. Now let us consider a reference frame, and let us just look at a particle in that reference frame. With time, the position of that particle will be changing, so there will be some delta dr and dt. But we basically know that whichever reference frame you use, c squared dt squared minus dr squared will be the same, whichever reference frame you use. Let us call this d tau squared. Or d tau is equal to square root of c squared dt squared minus dr squared, which we can also write as, well, let me just put a c squared over here also in the definition. 1 over c. This is equal to, if I just take out the dt out, This is square root of 1 minus u squared over c squared, where u, I defined it by dr by dt. Now this tau is usually called proper time of the object. So this is what we are imagining. Just pick up an arbitrary reference frame. In this reference frame, the object is moving with a velocity u. And in this reference frame, you just observe the object by a time, let's say dt. The proper time of the object is just in this calculated by the proper time passed for the object is calculated by the time passed in the reference frame multiplied by this factor where u is the velocity.
Hocam bu dt observation time.
You see, just let's see, you are moving around. I'm looking at you. Okay? So in my watch, the time that passes is dt. And in my reference frame, when I look at you, within this time, you move a distance dr. So this is the dt is the time measured by the observer. And of course, when I look at in your watch, how much time passes? It will be shorter, right? By how much?
İşte gamma çarpı t. Delta, gamma çarpı delta.
Gamma times or divided by gamma?
Gamma 1 bölü kök içinde bir eksi ve kare bölü.
Yes.
İşte doğru gamma çarpı t.
Gamma is larger than 1. Gamma is larger than. Remember, gamma is 1 over square root of 1 minus v squared over u squared over c squared. So this is always larger than 1. Now, you see, one nice thing about this d tau is, you see, if you look at its definition, the left-hand side is invariant. So should the right-hand side be. So this d tau is an invariant quantity. For example, I am one of the reference frames is fixed on me. Okay, so I look at the object, that's him, moving, let's say, with constant velocity u. I look at my time, let's say 1 second passes, so this is 1 second. I multiply that 1 second with 1 minus this v measured in my reference frame, so I obtain some d tau. Okay, then you are some other observer. You observe him you observe the two events that I'm comparing, they differ by 1 second in my reference frame. So I looked at him once and let's say he just blinks light twice. And between those two blinks, the time that passes in my watch is 1 second, his velocity is v, so I measure this quantity. You are another reference frame. So you look at him again, and again he blinks twice. You will observe the blinks. You look at your watch, you measure the time between those two blinks. You will measure this time difference, a different number. And you will measure a different velocity, different speed for him. But this product will be, this product calculated by you and this product calculated by me will be the same. It doesn't change if you change the observer. That is what we mean by invariant. It doesn't change from observer to observer. it doesn't mean conserved. You see, these are also sometimes confused. Conserved and invariant, they mean different things. Invariant means if you change the observer, nothing changes. Every observer obtains the same value. You are an observer, you measure his proper time. I measure his proper time, we will get the same value. Conserved means that there's a single observer, and that observer measures a given quantity at different times. So if that quantity at different times are the same, that means that quantity is conserved. A conserved quantity need not be invariant. For example, we know that energy is conserved. Just imagine a free particle, it only has kinetic energy. It might be moving in my reference frame with constant velocity. It will have one kinetic energy. It will have a total energy equal to its kinetic energy, which will be non-zero, which will be conserved, meaning that it will not change in time. But when you observe it, if you are moving relative to me, you will measure a different value of its velocity, different speed. So its energy, according to you, will be different. So energy is not invariant. It changes from frame to frame. Nevertheless, it is conserved. Now, let's see. I have the position 4 vector. It can be measured by whichever reference frame you prefer, x mu. I can look at its change in a given time interval, let's say. This is a 4 vector. I have one 4 vector. Well, this is nothing but the difference of two 4 vectors. And the difference of two 4 vectors is itself a 4 vector. This is nothing but the difference of the position 4 vectors of some object at two different times. Let me divide this by the proper time. Now, the tau itself is the same for every observer, for every reference frame. So if I would consider how this object transforms from one reference frame to another reference frame, tau will not change, but this will change. Only this one will change. So I need to consider only the transformation properties of that one. So let me define this by eta mu. Now in a different reference frame, eta prime mu, let's say, this is equal to dx prime mu by d tau. But I know what x prime mu is. This is d by d tau, lambda mu nu, x mu, x nu. But I am considering reference frames that are moving with constant velocity relative to each other. Remember, lambda mu nu depends only on the relative speed between the reference frames. It doesn't depend on the velocity of the object that I'm observing. So this is equal to lambda mu nu dx nu by d tau. Here I transformed x prime mu but not tau, because we had already seen that tau is invariant from reference frame to reference frame. But this tells me that eta prime mu is equal to lambda mu nu eta nu. You see, this is nothing but my eta nu. So eta mu is what we call the 4 velocity. It is the generalization of ordinary velocity to 4 dimensions. And this eta mu defined in this way this is how I define eta mu. This is a 4 vector. Saying that it is a 4 vector means that I know how it transforms.
Hocam şimdi burada mu kullandık, şurada mu kullandık.
You see, here there is a summation over nu. So it's just a dummy index. I'm just summing over nu. I mean, it just tells me what the components are. Mu can take values 0, 1, 2, or 3.
Hocam biz bunu nasıl hayal edeceğiz?
Which one?
Soruyoruz.
This is how you will imagine it.
Yani bir tane vektör var, komple 4 boyutta da mı hareket ediyor?
No, I mean, this is it. It is. I mean, just for every vector you have a 3-dimensional vector that is easy to visualize. You just assign it a 4th number. And both the 3-dimensional vector and the 4th number changes from reference frame to reference frame. Well, let's relate this to ordinary velocity. And there we can see why we are defining such quantities. You see, eta 0, let's start with eta 0. Eta 0 is dx0 by d tau. Well, dx0 is c dt. D tau is square root of 1 minus u squared over c squared dt. So this is c over square root of 1 minus u squared over c squared. This is my eta 0. Let us look at the other ones. Eta I. This is equal to dxi divided by d tau. This is dxi divided by square root of 1 minus u squared over c squared dt. This is equal to ui divided by square root of 1 minus u squared over c squared. Or let me write it in this form. The space components of eta, which is just an ordinary vector that is easy to visualize, it is given by the velocity of the object in this reference frame, in whichever reference frame you are considering, divided by 1 minus u squared over c squared. Now let us imagine we go to a different reference frame now. So you see here what we are doing. Well, let's just define what these dx's are. I'm the observer. I'm observing an object moving around. It has a velocity u. Now this dx mu is the change in the position for vector of the object that I observe. And d tau is the proper time that I calculate for that object. So now if I look at the 0 component of that quantity, dx0 by d tau, well, dx0 by definition it is just c times dt, dt being the time change that I am measuring. D tau is just this combination over here. So I just obtain that eta 0 is related to the speed through this relation. If I look at the space component, you see eta mu, I claim that it's a 4 vector. It has a space component, the zeroth component. No, it's a time component, the 0 component, and also the space components, the other components, the 1, 2, and 3 components. If I look at the other components, dxi is the change in the space position of the object. D tau is the same d tau. If I just put them over here, dxi is the change in the position of the object that I observe. Dt is the time that I observe. So dxi by dt is nothing but the velocity of the object that I observe. And that is ui divided by this combination over there. Let us all.
Şeyler değişiyor yani. Mesela hıza göre dx'ler değişiyor değil mi? Reference frame'e göre length.
Now this is just a single reference frame. I'm not yet switching to a different reference frame. I will do it in a moment. But this is just in one reference frame. Whichever one you started with. It can be, I mean, you first choose your reference frame in whichever problem you want to study. You can choose whichever frame you like. And in that frame, the object will have some velocity, some ordinary velocity, and this is the 4 velocity corresponding to its motion. And this 4 velocity, let's look at eta 0 squared minus eta squared. Well, eta 0 squared is just c squared divided by square root of 1 minus u squared over c squared. Minus eta squared is u squared over square root of 1 minus u squared over c squared. Now, there are no square roots, square. But you see, this is nothing but c squared. Well, it is constant. You see, if you go to a different reference frame, u will be different. So eta 0 will be different, eta i's will be different. They will all be different in a different reference frame. But nevertheless, they will be different in such a way that this difference is always c squared. Well, okay, let me put the minus sign over here, the plus sign over here, so this becomes minus. Now let's go to a different reference frame. In this new reference frame, let's say the new reference frame is moving with the speed c, with speed v in the x direction. So we already know how the 4 vectors change. Eta prime 0 will be gamma eta 0 minus beta eta 1. Eta prime 1 will be gamma eta 1 minus beta eta 0. Eta prime 2 will be eta 2. Eta prime 3 will be eta 3.
So, new velocities are greater than previous velocities.
I don't know. You see, you are saying that, okay, the gamma is multiplied by gamma, which is larger than 1, but you have a difference over there. It depends. Yes, that is what I assume. This is my S reference frame. This is my S prime reference frame. V is in the x direction, or the first direction. Yeah, the transformation of these etas from one reference frame to the other reference frame is kind of straightforward. We already know. Now let's try to calculate what about the velocities? This is the forward velocity. What about the ordinary velocities? How do the ordinary velocities change from reference frame to reference frame? Hmm? You see, in one reference frame, it will be dx prime by dt prime. This is how it will change in one of the reference frames. How we will calculate the velocity in the x direction, the speed in the x direction in one of the reference frames. Well, dx prime is nothing but gamma x minus v over c dx by v over c squared dt. No, minus v dt, sorry. Divided by, well, dt prime is gamma dt minus v over c squared dx. Just multiply the numerator and the denominator by dt. Gammas will cancel. So you get this is equal to u minus v divided by 1 minus vu over c squared. U prime is equal to u minus v divided by 1 minus vu over c squared.
Şimdi hocam, u dediğimiz bir referans frame, u prime öbür referans frame. V ne?
V is the relative speed of the two reference frames. You see, Galilean transformation just tells us that u prime is u minus v. This is the new term we have. Now, the thing is, if you look at the velocity addition rule, how velocity transforms from one reference frame to the other reference frame, well, it's quite complicated. This is a simple case where the reference frames are moving in a single direction, and the velocity of the object has only a single component. Well, we can also look at the other components. dy prime by dt prime, this will be equal to dy by gamma dt minus v over c squared dx. Which will be equal to well, no. I mean, you see, it just becomes complicated because we started by saying that it doesn't move in the y direction. If it doesn't move in the y direction, here you will end up having dy is 0. dy is 0. The y component doesn't change, so there's no y. But you see that, I mean, these expressions will change if the velocity is in some arbitrary direction. You see that if they are in some arbitrary direction, the velocity addition rule will become quite complicated. But if you use the four velocities, well, there will be more terms in these expansions, but you know what the Lorentz transformation matrix is. If you know the relative velocity of the reference frame, whatever the ordinary velocity is, whatever the velocity between the reference frame is, whatever direction eta is in, this is how they transform if u is moving in some arbitrary direction. Here, I already assume that my object is moving in the x direction. If it is moving also in the y direction, no, hold on. No. Okay, I'm just kind of getting confused. Okay, the object might have a velocity in the y direction. Nevertheless, these are the transformation rules. Y doesn't change. The t changes by this much. Here I have the x still. That is because my reference frames are moving in the x direction. So I can just multiply by 1 over dt, and this becomes uy prime is equal to uy divided by gamma 1 minus v over c squared ux, and uz prime is equal to uz divided by gamma 1 minus v over c squared ux. You see, this u can be in arbitrary direction. Nevertheless, the transformation laws for uy, the y and the z components depends on the x component of the speed, ordinary velocity. Now, long story short, you see, these are quite complicated transformation laws for ordinary velocities. But for this 4 velocity, it's just like any other 4 vector. These are the transformation rules. Now, if you follow the argument of the reasoning of our first year kinematics course, you see, if you remember in 109, what we did was we first discussed the position vector. Well, here now we have the position 4 vector. Then we discussed the velocity vector. Well, now we have the velocity 4 vector. The next thing that we should define, momentum. We can define the momentum 4 vector. It will be just m times the velocity 4 vector. And p squared is m squared eta mu, which we had just calculated to be minus m squared c squared. So p squared is also invariant. Now let's see what the components of this p are. Now p0, let's start with pi. Pi is m times eta I, but eta I, we had already calculated it. It's just the velocity divided by square root of 1 minus the velocity of the object, by the way. You see, we have many 1 minus u squared over c squared factors. We also have gamma, which is 1 minus v squared over c squared. Gamma, the v appearing in gamma is the relative velocity of the reference frames. The u appearing over here is the speed of the object observed in a single reference frame, whichever frame you choose. M times u I divided by square root of 1 minus u squared over c squared, or p is m times v divided by square root of 1 minus v squared over c squared. Well, you see, in 109, in mechanics courses in your freshman years, this was what we had defined as the momentum, linear momentum. Now we will identify this combination as our linear momentum. Now let's also look at the zero component, P0. This is m times eta 0. Well, we had already calculated what eta 0 was. Now you see, this is where we define the eta 0. It is just c over that square root, mc over square root of 1 minus u squared over c squared. This is, by the way, nothing but energy of the particle divided by c.
Why is it equal to MC?
Huh?
For example.
M?
Why is it equal to MC? Why not, for example, MU or MUX? Are you assuming that the particle is moving?
No, I'm not, you see, I'm not assuming anything. I'm just following my definitions. You see, these are my definitions. I first define the for velocity. That is my definition of the for velocity. And then I studied its components. What are the components of these four velocities? And we found out that the zero component is just the speed of light divided by that square root. So if you just multiply this by m, that is how we define the momentum. I just define the momentum as m times eta 0. But that is my eta 0, so that is c. The u, or the velocity of the object, appears in the other component. Sorry, I made a mistake over here. This is not v, this is u. I repeat, u is the velocity of the object in the reference frame that you are looking at it. The total energy of the object. Well, let's look at the kinetic energy. We define it as mc squared over square root of 1 minus u squared over c squared. The kinetic energy, you see, energy of the object when it is at rest is mc squared. Now, when we talk about kinetic energy, we usually understand the energy due to the motion of the object. But this mc squared is not due to the motion of the object. So if you want to define the kinetic energy, we define it as mc squared over square root of 1 minus u squared over c squared minus mc squared. Now let's calculate this one. This is equal to mc squared times 1 minus u squared over c squared minus mc squared. Here I have minus 1/2. Let me take the approximation that u over c is much, much less than 1. So I'm in a reference frame in which the object is moving slow compared to the speed of light. So this just becomes mc squared 1 plus u squared over 2c squared minus mc squared. Well, this 1 is cancelled by this minus mc squared over there, so we end up having 1 over 2 mu squared. This is the non-relativistic kinetic energy of the object that we are already familiar with. Well, let's see. Did I assume anywhere that my object is small? In which step did I assume that it is small? No, did I make that assumption? No, I didn't assume anywhere that the object is small. But of course, I'm ignoring any kind of rotational motion of the object or deformation of the object. Those things I should add. So as long as my object is not deformed, my object is not rotating, I can specify its position by just choosing a reference point on my object and saying that, okay, the position of that point is the position of my object. You see, here I'm not looking at the potential energy. I'm only looking at the kinetic energy. I'm not looking at any forces here. There are no forces yet. You see, the problem with the forces, that we will come in a moment, is, you see, potential energy is basically the interaction between 2 points. So you have an object over here, another object over here, and due to their configuration, you have a potential energy. And you form action-reaction pairs. Now, we have seen that signals travel at a finite speed. So how do you define the potential energy to start with? How will we define, I mean, we will eventually define forces, etc., but can we really specify a potential energy in electrodynamics? We had seen that electrostatic potential doesn't really make any sense in the sense of conserved energy. We said that we cannot define it in electrodynamics. So what kind of potential energy can we define? So now definition of the potential energy in relativistic frameworks is always problematic. It's hard to define a consistent potential energy. So that's why we will be avoiding defining potential energy. So here there's no external force acting on the object, there's no potential energy, etc. It's only my object moving around in a reference frame.
Ama gravitational force var.
You see, in a relativistic framework, things get complicated. You can, of course, add the gravitational force, but as a field. So not in the sense of Newton's gravitational force. We cannot add it because it doesn't respect the constraint that the signals should travel at a finite speed.
Ama mesela kara deliğe çok hızlı bir şekilde yaklaşıyorsa.
Okay, so
Yani onun gravitation çok yüksek.
of course you can define the gravitational effects, but it won't be in the form of just adding a potential to the energy. That's what I'm trying to say.
O zaman bizim toplam enerjimiz sadece kinetik enerjiden mi olur?
Plus the rest mass energy, mc squared.
Bu da velocity sıfırkenki kinetik enerjisi.
No, that is the energy, you see, the kinetic energy is this one. This is my kinetic energy. This is how I define the kinetic energy. Now, mc squared is what's called its rest mass energy. So it is the energy the particle has when it is at rest.
O zaman bu cisim de burada duruyor. Potansiyel enerjisi var.
Fine, add it.
O zaman yani bunun potansiyel enerjiyi eşitleyebilir miyiz? Yani siz
You can say that its mass is larger due to the potential energy. Fine. But it's not so straightforward. That's what I'm saying. Just don't take that too literally. For example, when you are talking about the mass of the proton, now the quarks making the proton, if you sum their masses just make, I don't know, like a few % of the mass of the proton. The rest of the mass of the proton, the rest mass of the proton is the kinetic energy of the quarks moving inside the proton and the potential energy of interaction between the quarks inside the proton. So if you have any potential energy, you can add it to the energy. But just be careful. Don't take it to extreme limits. So here, there's no potential energy. We are not considering the potential energy here. Yes, the mass is energy. Energy is mass, in a sense. Now, there is another thing, let's clarify before you go for a break. You see, P is equal to mu over square root of 1 minus u squared over c squared. E is m over square root of 1 minus u squared over c squared times c squared. You see, this combination appears quite often, which you can say that m effective is m effective or m relativistic if you want, m over square root of 1 minus u squared over c squared. And quite often you hear that an object, if it goes close to the speed of light, its mass increases. I'm sure you have heard of this quite often. Objects get heavier as they get faster. As they get faster. For you, the object is getting faster, its mass gets larger. Those are the sentences that you hear. But whenever you are talking about the mass, let's say the mass of the object, this is m, which is constant, does not depend on its speed. So whenever we are talking about the mass of the object, it is this one. And this definition is no longer used. The relativistic mass or the effective mass or whatever you want to call it, it's not used. No. We will see. Why not?
Şöyle hani efektif kütle diyoruz, kütle constant diyoruz, enerji artıyor. Ama şey olmasın, korunun gerekiyor.
Energy will be conserved. There's no problem with that. Momentum will also be conserved.
Ama peki geri dönüşte yani kütleyi parçalarsam da enerji elde ediyorum.
Okay, so
Yani tersini düşünürsen eğer, hani o kütleyi ortadan bir şekilde kaldırırsam, parçalarsam, o zaman konserve olmamış olur. Yani tersi düşünmüyorum.
you see, energy is mass. So energy conservation, ignoring mass, has no meaning. Just like mass conservation, ignoring energy, has no meaning. Energy, in the sense of all the energy of the system, including the rest mass energy of the system, is conserved. For example, in reactors, let's say, what we do is we split nuclei and extract energy. Now, the total rest mass energy plus the extracted energy is conserved. The sum of the masses of the mass of the nuclei before it splits is larger than the sum of the masses of the nuclei after it splits. Masses meaning their rest masses. The difference is the energy that we extract. Energy and momentum is conserved. Okay, I will just ask you one more question before you go to think during the break. Okay, momentum is conserved. For velocity, we said, okay, there is the ordinary velocity, there is the forward velocity. For momentum, why not make that same separation? There is the ordinary momentum and the forward momentum. And claim that maybe m times u, we should just call it the ordinary momentum. And p is the forward momentum. Which one is conserved?
One seems to correspond same. One seems to correspond same.
But you see, ordinary momentum, if it is conserved in one reference frame, it will not be conserved in a different reference frame. But forward momentum is conserved in every reference frame. That is why when we are talking about the momentum of the object, it is always this one. We don't really talk about that momentum. But ordinary velocity and forward velocity, they correspond to different things. Different things that make sense on their own. So that's why we just make that separation. We still keep both of them. But for momentum, the concept that makes sense will be the forward momentum. And Newton's second law will also be correct, given that P is the forward momentum. Well, Newton's first law still makes sense. It defines the inertial reference frames. Newton's second law is slightly modified to take this form. Newton's third law doesn't hold. Action-reaction. It cannot hold. Basically because it says that, you see, if you have two objects, if they are at rest, no problem. So the forces will be backwards and pointing towards each other. Well, not necessarily backwards, but they will be, if one is exerting a force in this direction, the other one will be exerting in the opposite direction. But if the objects are moving, you see, this will only feel the retarded position of the other object. So the force that this will feel will be either towards or against or related with the retarded position, not the current position. So you just cannot talk about action-reaction pairs.
Yani aslında etkisini sonradan hissediyor.
That is due to the finite speed of light.
Peki simetrik bir reference frame seçimiyle yapamaz mıyız?
Okay, maybe in one reference frame it will be satisfied, but we are looking for laws that are valid in every reference frame. So in that sense, Newton's third law is not valid in every reference frame. As you said, you might be able to find some special reference frame in which it will hold for two particles. But if you, let's say, have four particles, each exerting forces on each one, maybe you will find a reference frame in which just a pair just exert action-reaction forces, but the other ones will be just, they won't form action-reaction pairs. Okay, let's give a 10-minute break, then we will continue.